Hello, this is Mrs. Brown, and today we're going to be looking at systems of equations, solving them using substitution. So here are the steps kind of broken down. We'll look at an example as we kind of go through, talk about the different types of solutions, and then we'll finally finish by doing a couple of examples. Okay, remember that it's a video, so you can pause and write things down that you need to if I'm talking too fast or moving on. So I'm not actually going to probably spend enough time for you to write everything, so you may want to pause it as we go through. All right, so steps to solving systems using substitution. The first step is you have to make sure that one of your equations is solved for just one variable. So for instance, this is not solved for a variable right now. You have 2x plus y equals 3. So since the coefficient of y is 1, I would probably solve for y, which means I have to get rid of 2x. So in other words, I'm kind of making it into slope-intercept form. So if I take 2x plus y equals 3, and I subtract 2x from both sides, that comes out to nothing. And I'm going to go down here. I get y equals negative 2x plus 3. Okay, and so now I've solved for y, so y is all by itself. That's really important when you are solving systems using substitution. You have to have one of your equations solved for a variable. All right, so sometimes it'll already be solved for you and you don't have to do step one, so it just depends. Number 2, substitute in the equivalent expression for the variable you solve for in step 1 to the other equation. So I actually only wrote one equation up here, but we have a system and we're trying to figure out the answer to this system of equations. And so since I solved for y here, the equivalent expression is this. This is equal to y, because y is by itself. So what I would do is I would take this expression and I would substitute it into the other equation. And that's what's going to allow me to find the answer. Why am I doing that? Because I'm trying to get rid of a variable. I can't solve an equation and find a one single answer if there are two variables in the equation. So if I can get rid of one of them, which is the purpose of substitution, then I can actually solve because I'll have just x's or just y's. And if I have just x's or just y's, I can solve for that particular variable. So if I go, I would take my 3x minus, okay, one of the things that you really need to get in the habit of doing is when you substitute in parentheses. Okay, so instead of y, I'm going to replace it with this. With addition, it's not a big deal, but when you have a subtraction, especially because we're going to have to distribute a negative, or if there's a coefficient other than 1, you're going to have to distribute that number. So if you get in the habit of always substituting it into parentheses, you're going to make less mistakes, and it'll just be easier overall. Now, even though this looks a little bit complicated, we have a single equation, a single variable in a single equation, and we can solve that. Okay, so let's look at the next step. All right, so this is what we just wrote on the previous page. And so step 3 is just solve that equation. Okay, so what do we need to do? Well, first of all, I need to distribute this. Remember, this is like -1. So I'm like multiplying through by -1. If I think about that like this, so I've got 3x, that doesn't change. And then -1 times -2x is a positive 5, because a negative times a negative is, I'm sorry about that, I already combined it in my head, a positive 2. When you look at that, negative times a negative is a positive. I'd already add those together in my head. -1 times 3 is -3 equals 12. Okay, so from there, we combine like terms. So 3x plus 2x, 3 xylophones plus 2 xylophones is 5 xylophones, minus 3 equals 12. I can add 3 to both sides. So I get 5 times x equals 15. The opposite of multiplying by 5 is dividing by 5. And so once I've done that, I end up with x equals 3, because 15 divided by 5 is 3. So that's half of my answer. But remember, there were 2 variables. So now I have to go back and figure out the answer to the other variable. So substitute in the answer that we got. back into one of the original equations to find the other variables. So you can pick either one and you should end up with the same answer. So if I substitute 3 in here, I get 3 times 3 minus mystery number equals 12. Well, 3 times 3 is 9. Okay, in order to move the 9, since it's positive, I'm going to subtract it. I end up with negative y equals 3. And of course, I'm not allowed to have a negative number. This is the same as a coefficient of negative 1, so I can't leave it that way. So I can multiply by negative 1, which changes that to y. And 3 times negative 1 is negative 3. So I get my two answers, and I would write that as a point. So my final answer would be the x-coordinate is 3, because remember the solution to a system is a point. So I would write that in that form. Okay. So let's take a look at a couple of the types of answers. So most of the time you're going to come up with a single point, but sometimes there's weird cases of strange things that happen. Okay. Well, I think I can flip this. Okay. So if I take a look here, the types of solutions that you might run into. So one solution is a point, x, y. That's like the example that we just did. It comes down and you should write your answer as a point. Okay. Well, what are the weird cases? What are strange things that happen? One of the things is an infinitely many solutions. And what this means is the two equations are actually the same line. They represent the same line when you graph it. So if it's the same line, when you solve it, the variables are all going to cancel out and you're going to get something weird like 5 equals 5. Well, is it true? Does 5 equal 5? Sure, it does. Therefore, it's infinitely many solutions. The other situation that you get that's weird is no solution. This means that the lines are parallel, and since the solution is the intersection of where the lines meet, whether it's a single point or the same line, if it's infinitely many, by definition, parallel lines are never going to meet. So they are always the same distance apart, they never intersect. So therefore, there's no solution to a system because there's never going to be an intersection point. And what happens is, again, your variables are going to cancel out, but this time you get something that's false, something weird like 0 equals 7. Well, you know 0 doesn't equal 7. That doesn't make sense, which means there's no solution. That's your clue in that these are parallel lines. You're not going to have a solution to that. Okay, so you're either going to get a single point. Most of the time, this is what's going to happen. Occasionally, everything's going to cancel out, all the variables, and you're either going to get something that equals itself, which means it's infinitely many, or something that equals something that it's not, which is going to be no solution. So let's take a look at what each of those appears when we solve it. All right, so if I look at these steps, this is already solved for y. So since it's already solved for a variable, I don't have to solve for that. So I'm going to look at what y is equivalent to, in this case, x plus 1, and I'm going to go ahead and solve it by substituting it in for y. Again, I'm going to get in the habit of always substituting into parentheses. If I look, do I actually have to distribute anything? Well, no, it's a plus sign, and y didn't have a coefficient other than 1, so 1 times x is x, and 1 times 1 is 1. So really, I've just got 2x plus 1 equals 4. So I didn't really need the parentheses that time, but you often do. So always substitute into parentheses, and you'll make less mistakes. Okay? Remember that if the coefficient is not listed, the coefficient is 1 because 1 times that number is not going to change the value. So I have to combine like terms. So 2 xylophones plus 1 xylophone is 3 xylophones. I subtract 1 because I get rid of the addition and subtraction first. 3 times mystery number equals 3. So x equals 1. Now that I've solved that, I substituted it in, I've solved it. Now I have to go back to one of my original equations. It doesn't matter which one because it will work for either one. And I substitute in 1 for x. So I'm going to put it in this one, the x plus 1. So 1 plus 1 and 1 plus 1 is 2. So I think my answer is that when x is 1, y is 2, and that would be the system solution. I can check my answer really easily by substituting that in to the other equation that I didn't just use and make sure that it works, because that point should work for both equations. So if I do that, if I take my 2x plus y equals 4, and I substitute 1 in for x, and I substitute 2 in for 4, does that really come out to 4? Well, 2 times 1 is 2, plus 2 is in fact 4. So I know that I did the problem correctly because my point works in both equations. So it's pretty easy to check your answer for this because it has to work in both. Okay, let's take a look at another possibility. All right, so when I'm looking here, these are not solved for, neither one is solved for a variable. But this one's close because I have a variable on one side, it just has a coefficient other than 1. So what I want to do is divide out by 2, and then y will be all by itself, and I can use that to substitute in. So I'm going to start by dividing all of these by 2. This cancels out, so I end up with y. 4 divided by 2 is 2, and 6 divided by 2 is 3. So this is one of my equations. Here's my other equation. Now, since this one is solved for y, I'm going to take that equivalent expression, so what y equals, and put it in for y in the other equation. Okay, so 6x minus 3, and I'm putting it into parentheses. It's really important that you put it into parentheses. 2x plus 3 equals negative 9. Okay, so again, I'm thinking of this as a negative 3. I'm going to distribute negative 3. Negative 3 times 2 is negative 6x, and negative 3 times 3 is negative 9. I still have a 6x here. Okay, well, when I combine like terms, I can put the x's together. If I have 6x minus 6x, I have nothing. It's 0. And I end up with negative 9 equals negative 9. Well, that's a true statement. All the variables have canceled, so this is a case of infinitely many solutions. In other words, these two equations are really the same line. And I can prove that. I can take this, if I look at 6x minus 3y equals negative 9, right? So these are all divisible by 3, so let's divide out by 3. Okay, that's going to be 2x minus y equals negative 3. Okay, if I want to solve for y, I get rid of 2x on both sides. So I end up with negative y equals negative 2x minus 3. I want to multiply 3 by negative 1 because I can't leave y negative. Negative times a negative is a positive, and a negative times a negative is a positive. And you can see that this equation is the same as this equation up here. So they are, in fact, the same line. Okay. All right, let's look at one more example. Okay. When I look at this one, it actually is solved for a variable. It's backwards. It's solved for x this time. So instead of substituting something in for y, I'm going to substitute in for x because I have an equivalent expression for x. X equals 2 times y. So let's see what happens when I substitute that in. So again, I'm going to replace x this time with 2y. I'm substituting it into parentheses always. Get in that habit. Make less mistakes. Minus 6y equals 12. Okay, 3 times 2 is 6. Well, 6y minus 6y is nothing. Equals 12. Well, this is false, obviously, because 0 doesn't equal 12. So this is why there is no solution. These lines are, in fact, parallel, which means they have the same slope. We could put them in slope-intercept form, and we could see that they actually are both going to come out to a slope of a half. And since they both have the same slope, they're parallel lines. Okay, I hope this helps and have a great day.